Alright guys, let's get rolling with vodcast 7.4. We're going to talk about types of reactions. For those of you in the CP class, this will be our last section for Unit 7. There are some things that if you looked at the curriculum guide that are in Unit 7 that we haven't done, but we've done them already, like oxidation numbers and stuff. So this will be it for us in the CP class. For those of you all in the honors class, we've got one more unit after this. But this is still a pretty key unit overall. And so the unit is about exactly what it sounds like. It's about different types of reactions. So we're going to jump right in and start talking about the 5 major types of reactions. So first off, we have synthesis reactions. These are not always called synthesis. Sometimes they're called combination reactions. Okay? As with a lot of these things, sometimes you have a whole bunch of different names for them. And essentially what a synthesis reaction is you've got 2 or more things, and they're going to combine, and they're going to form a single product. And that's why it's sometimes called a combination reaction. And so, as you can see here, I've got a potassium, okay, and it's going to react with gaseous chloride, and it's going to form potassium chloride. Potassium chloride has a couple of uses. It can be poisonous in high doses. In smaller doses, it's actually often used as a salt substitute for a low salt. I know low salt, that doesn't make any sense, but low sodium salt, I guess, would be more appropriate. And so that's what a synthesis reaction is. Now, what's going to be really important to us in this reaction section is not just knowing sort of like what the definition is, but being able to recognize these reactions. It's all about being able to identify them. So for each one of them, I'm going to give you a key thing that is sort of your identifying mark to look for. So in this case, the key is that there is one product. Okay? So I had 2 reactants. I could have more than that. But on the product side, on the right-hand side of the reaction, there's just one thing. And I know you're thinking, well, what about this 2 here? I mean, there's one chemical. You might have more than one molecule of it, or more than one mole of it, but it's one single chemical by itself. Okay, so that's your key to indicate that it is a synthesis reaction. Okay, so that's synthesis. The opposite of synthesis, or at least sort of the opposite of synthesis, is what we call a decomposition reaction. Decomposition basically means sort of what it sounds like. It means that things are breaking apart. And so whereas a synthesis was 2 things turning into one thing, a decomposition is basically the opposite. It's going to be one thing, a single compound, okay, one thing, breaking down into 2 or more things. And if you notice here, we haven't really talked that much about this, but a lot of times you'll see in chemical reactions, you'll see something just above the yield arrow. And what that is it can be any number of things. It can be a catalyst, or it can be the conditions under which it happens. And so what this one is telling us is that if I take calcium carbonate and I heat it, then I get calcium oxide and carbon dioxide. Okay, so what's the key for this one? Pretty simple, and again, pretty much the exact opposite of a synthesis reaction. The key here is that there is one reactant. So there's one thing to the left of the arrow in a decomposition. There's one thing to the right of an arrow in a synthesis reaction. Okay, so those are really sort of the 2 that are easiest to recognize. I mean, if you see one reactant, you immediately think decomposition. If you see one product, you immediately think synthesis. Okay, so that works out pretty simply. The next major type of reaction is what's called a combustion reaction. And again, it's pretty much what it sounds like. Combustion implies burning. And so in a combustion reaction, you have some compound that is going to burn. And what burning means in a chemical sense is that something is combined with oxygen. Okay? And when that happens, it's going to give off energy, okay, as light and usually as heat as well. Sometimes the heat's a little less recognizable, but usually as light and heat. So like when you're burning a log in the fireplace, that's a combustion reaction. You're doing combustion on that wood. It's turning from the chemicals that make up the wood into carbon dioxide and water, and it's giving off a lot of heat in the process. Okay, so what's the thing in this one that is the giveaway for us? Well, the key in this case is that oxygen is a reactant. That's sort of what we said in the first place here, is that oxygen should be one of your reactants, not one of the products. It should be one of the reactants. You can't have a combustion reaction without oxygen. Okay, now the oxygen can come from different places. In fact, there are some reactions like the thermite reaction that the oxygen is not separate, that it's actually part of the chemicals that cause the reaction. But in most cases, you're going to have O2 by itself as one single thing, and then it's going to be combined with something else. What it is usually combined with is this, which is called a hydrocarbon. Not necessarily this molecule, which is methane, natural gas, but some molecule that has carbon and hydrogen in it. Hydrocarbon. And that would be like gasoline is a good example. Kerosene would be another one. Natural gas, butane, propane, those are all hydrocarbons. And usually those are what react with the oxygen in a typical combustion reaction in Chem 1. If that's what reacts, if it's a hydrocarbon plus oxygen, then you always get these two products. Now, we're not going to worry too much about products right now, but this is what the products would be if it's a hydrocarbon plus oxygen. You always get carbon dioxide and water as your products. Okay? Now, there are cases where you can have a combustion reaction that is not a hydrocarbon, and this is a pretty good example of one, and we're going to actually work this one out in the lab a little bit later on. Don't know what is going on there, guys. But this is magnesium plus oxygen. It's going to yield magnesium oxide. If you remember the video clip from earlier in the year, and maybe these video clips will be in when I do the re-editing on this video, where I took a magnesium strip and lit it on fire, so the magnesium combined with oxygen. And then what's left is sort of this white powdery stuff at the end that is magnesium oxide. We're going to do this lab in a couple of weeks where we're going to burn this stuff in a crucible and we'll do this combustion reaction. Okay, so the harder types of reactions to recognize are two types of reactions called replacement, or sometimes they're called displacement reactions. So in the first one, in a single replacement reaction, what happens is that we have a single element, okay, one element, and it's going to take the place of another element in a compound. So it's a single element by itself, okay? So it's usually it's either a metal as a solid or it's some sort of gas that's by itself. And that metal is going to replace another metal, okay, and basically kick it out of its place. Now, we'll talk later in some other parts of the class about when this would replace. There's a thing called an activity series. Basically, it just means that magnesium, if it's more reactive than zinc, it's going to take zinc's place. So what happened here is magnesium on the product side is now combined with nitrogen, or I'm sorry, nitrate. Now what that means then is that it replaced zinc, and zinc is now alone and by itself. And so when we talk about the things that identify a single replacement reaction, what identifies it is that you have a single element as a reactant, and then you have a different single element as a product. Okay, that's what you're going to get as your results there. So single element as a reactant, different single element as a product. Okay, that's a single replacement. And again, the whole reason that would happen is that the magnesium is more reactive than the zinc. Now, obviously, you would need some way of knowing which thing was more reactive, and we'll get into that a little bit later, especially in the honors class. Okay, so last type of reaction that we have to worry about are called double replacement or double displacement reactions. Now, what's happening here, if in a single you have a single element by itself switching, what happens in a double replacement is that you have two elements, particularly two cations. Okay, if we broke these compounds up, this would form sodium plus and cadmium 2 plus. So those are the two cations. Remember that cations are things that have a positive charge, and they're going to switch places. So what that means is that the sodium wants to come over here with the nitrate, and that the cadmium wants to come over here with the sulfide. Okay? Now, if you look over on the product side of the reaction, that's what's happened. We have cadmium sulfide, or cadmium 2 sulfide rather, and then we have sodium nitrate. Okay? Now, you'll note that in the definition it says two aqueous ionic compounds, and that's technically sort of the easy way to tell that this has happened, is that there are two aqueous compounds. So if you look at the reactants, we've got an aqueous compound here, and we've got another aqueous compound here. But really, most of the time when we're going to work these out, the phases aren't given a whole lot. So how then would you know that it was a double replacement? Here's the way you really want to think about it. And maybe instead of aqueous, maybe a better thing to think about is that if you replace that word aqueous with the word ionic. Now, It does really technically, it's pretty much always going to be aqueous, but again, we're not going to see the phases. So what you guys are going to recognize is you're going to look at a reaction, and it's going to have two ionic compounds on the reactant side, and then two different compounds on the product side. By different, I mean that things have switched places. Okay, so again, what's going to happen is that sodium is going to come with nitrate, okay, sodium nitrate, and that cadmium is going to go with sulfide, and that gives me cadmium sulfide. Okay, so it's basically a double swap, where in a single replacement it was just sort of one thing kicking out the other. All right, so those are our 5 types of reactions. Now, real quick, what I want to do is I want to run through examples of what we're going to have to do to identify different types of reactions. So this is what we're going to work on in class today. And this is kind of going to be a big part of the test, aside from the balancing and naming stuff when we get to that test as well. So how does it work? So you want to look at each equation. These are ones from our balancing worksheet, so don't worry about the blanks, but I'm going to look for the things in each of them that identify them, okay, that let me know what type of reaction it is. So in number 1, N2 plus H2 gives me NH3, okay? That is one product, and one product is going to mean synthesis, okay? In number 2, we got potassium chlorate yields potassium chloride plus oxygen. One reactant is a decomposition, okay? So remember, we had one product is synthesis, one reactant is decomposition, okay? So number 3 is a little bit tougher. In number 3, I've got sodium chloride, so it's an ionic compound. This is not an ionic compound, though, so I know it can't be double. But what this is a single element by itself. And then on the product side is another single element by itself. And so when you see those singles, that should sort of let you in that that is a single replacement. Okay? Now, for number 5 here, and I know we skipped 4, that's because I cut out some of the ones from your worksheet. I've got silver nitrate. That is an ionic compound. Magnesium chloride is another ionic compound. And if you look at the products, it's not magnesium chloride now, it's silver chloride, meaning that silver and magnesium have switched places. Magnesium is with nitrate now, okay, and silver is with chloride now. If 2 things switch places, then that is what we call a double replacement reaction, okay? So, not too bad there. If we look at number 6, okay, ionic compound, that's probably a pretty good hint that it's double replacement. You just want to check what switches. So potassium is now with bromine, okay? Aluminum is now with sulfate over here, and so that is definitely a double replacement reaction. All right? Now, 7, 8, and 9, all the same thing, okay? And I can circle one thing between all of them and make it real easy, okay? All of them have oxygen as a reactant, okay? Anytime we have oxygen as a reactant, that means that it is a combustion reaction. Now, there's a couple other good hints that it's combustion. The oxygen is the dead giveaway. That's always the thing that you should look for. But the other pretty good hints are that there are hydrocarbons as products. Hydrocarbons are usually going to undergo combustion reactions as far as what we're doing. And then when you get to the product side, the products on all of these are carbon dioxide and water, and that's always the products of hydrocarbon combustion. Okay? So again, as usual, we'll walk through some of these in class, get some practice on these. You can certainly ask for some help on each of these, but what you really want to key in on are what are the key points. So synthesis, one product; decomposition, one reactant; single replacement, a single thing by itself, and then another single thing at the end, a different one. Okay, double replacement, 2 ionic compounds switching their cations. And then combustion, oxygen is a reactant, usually with a hydrocarbon, but not always, and CO2 and water as products. All right? Thanks as always, guys.